Alrighty, so this video we're going to work out some example problems for this chapter 4, which deals with reactions. So if you remember, we introduced in the last lecture the fact that when you have a system, so a truss, a bridge, a frame, something like this, generally you have to support it, whether it's on the ground or it's hanging from the wall. It's supported in some way. And we saw that there are three basic types of supports. The first is called a pin support. And when you have a pin, you can have a vertical and a horizontal reaction. Call it Ry and Rx. So what the pin does is you basically think of it like it's a bolt. You've bolted this bar into place. And so if I try to pull the bar to the right, the pin holds it in place. So that means as I pull to the right, the pin pulls back to the left, preventing me from moving the bar. Or if I try to push down on the bar, the pin is holding it up, preventing it from falling, so the pin reacts by pushing upwards with a reaction. The second type of support is a roller. So, you can think of it like skateboard wheels or something like that. Basically, what this does, it's called a roller, is if this is the support, and so literally think of a skateboard. If you have a skateboard, here it is, and you have the wheels. Well, if I try to pull the skateboard to the right, the wheels allow the skateboard to roll, so there's no reaction. It's just allowed to move to the right. However, if I stand on it, so I'm pushing down on the top of this bar, this skateboard, well, those wheels are on top of the ground, and obviously the skateboard doesn't fall through the ground, so there's a reaction by the supports, by the wheels, to push up. Now in physics we call that a normal force, but here it's just a reaction by the support, and so for rollers you always have the perpendicular reaction. Now, in the way I drew the roller, of course, the reaction is vertical, so I'd call it Ry. But you could easily have the roller on like you'd have a system like this, where this side over here is a wall, this is the ground, and you have this kind of L-shaped bar, where over here is a pin, and over on the wall, the vertical wall, is a roller. Well, for that, notice that the vertical reaction would be horizontal in that case. It's always perpendicular to whatever the surface is. Okay, so don't just memorize, oh, rollers are always vertical. Well, no, it depends on how the roller is oriented. If it's oriented normally on the ground like this, then yeah, the reaction is vertical. But if the roller is on the wall, a vertical surface, then it's horizontal instead. Alright, and lastly, the final type is just a normal kind of fixed support. So the bar is just hammered into the ground, a telephone pole or something like that, or a basketball goal. The thing is dug into the ground or cemented into the ground or something. This is called a fixed support. And if you think about trying to apply forces to this, if you try to push this pole to the right, it doesn't want to move to the right, so it reacts back, so you'll have a horizontal reaction. If you try to push down on this pole, of course, it doesn't want to go down into the ground anymore, or you try to pull up, it can't get pulled up out of the ground, and so there must be some vertical reaction. But then finally, if you were to push on this pole, let's say you push horizontally, generally speaking, it would want the pole to kind of rotate downwards, rotate clockwise or something. But it doesn't want to. It's cemented into the ground. So there's going to be like a rotational reaction called a moment reaction. And so there's also a moment reaction. So 3 reactions for the fixed support. The horizontal one, the vertical one, and a moment one. So that's what we saw last time, these types of supports. And what we're going to do is have a number of problems where we have some system, I don't know, it could be a plank of wood, it could be a frame, whatever it is. It'll be supported. We're going to stick some load on it, some set of forces. And all we want to calculate is what are the reaction forces? What are the forces of reaction at these supports? So let's start with one. Let's say we have a nice plank of wood, and I will support it like this. Okay. I will call this point A, this is point B, and then there will be a load, let's say 100 newtons here, let's say 50 newtons here, and 20 newtons here. And now we need our distances. Let's let from here to here be 2 meters. Here to here be 3 meters. And here to here is 5 meters. All right, so there's our system. Plank of wood, kind of like a diving board or something. It's supported at 2 places, at point A and point B. And there are 3 loads on this system. Some of the forces are pointing down, some of the forces are pointing up. We're going to have to keep track of this. And we know the distances involved. We know where the forces are located relative to the supports. So the question would say, calculate the reactions. All right. Well, in order to do this, I first, of course, have to figure out what are the possible reactions. Well, let's look at point A. Support at A is a pin, and I know that a pin means there could be a vertical and there could be a horizontal. So some AX and some AY. Now, can I tell which way they're going to point? Because, of course, the horizontal one can point either left or right, and the vertical one can point either up or down. Do I know? Well, it's not necessarily clear, because some of the loads are pointing upwards, some of them are pointing downwards. If I don't know for sure, I'm just going to guess. I'm going to guess that the vertical one at A is up, and the horizontal one will be to the right. Okay? I'm just choosing. I don't have any insight. It's not a magical guess. You'll see if I happen to be wrong, then when I get a reaction force, it's going to come out to be negative. So I just say, okay, because it was negative, flip the direction. But if I guessed right, it'll be positive and I don't have to do anything. So I've guessed the vertical at A is up and the horizontal at A is to the right. Now what about at B? What are the possible reactions at B? Well, B is a roller, and I know there's only the perpendicular reactions, and so that's going to be a vertical reaction. Again, I'll go ahead and guess that the vertical reaction at B, By, will be upwards. All right, so now I know what I need to solve. I need to solve AX, AY, and BY. That's my three unknowns. What equations do I have to be able to solve these unknowns? Well, I've got the sum of the forces in the x direction better be equal to 0. The sum of the forces in the y direction better be equal to 0. And the sum of the moments is equal to 0. What these equations tell me, the first one, is this plank, this whatever it is, this system is not moving left or right. It's in equilibrium. It's not moving. And if it's not moving, there better not be any forces or any net force in the x direction. Because if there is a net force in the x direction, then it's accelerating in the x direction, which means it's moving. And of course, the same goes for the other two. The sum of the forces in y direction being equal to 0 just tells me this object's not moving up or down. And the sum of the moments equal to 0 means this object is not rotating. And that's what we're going to assume. That's why this part of engineering is called statics. The system is not moving, it's static, it's in equilibrium. So all the forces and all the moments must add up to 0. All right, so I've got everything in place. Now it's time to start solving. I've got three equations to start with. I always start with the moment first. So let me do the sum of the moments equal to 0. But in order to solve this, I need to know what is my point of rotation. Because in order to calculate a moment, I need force times distance, and distance is the distance to the point of rotation. So, should I choose point A to be my point of rotation or point B? The rule is, when you solve for the moment, you always choose the point of rotation to be where there's the most number of unknowns. Well, point B has one unknown, point A has two unknowns, so obviously I'll choose point A. So I'm doing the moments about point A. So all of the distances are relative to A. And then I'm also going to choose, when I calculate a moment, all forces that cause a counterclockwise rotation will be positive moments. Forces which cause my system to go clockwise will be negative moments. I'm choosing that. You could choose the opposite. That's fine. You're going to get the same answer. But engineers, mathematicians, and physicists all choose counterclockwise to be positive. It's the right-hand rule is the reason for that. Anyway, let me go ahead and calculate. So I'm looking at point A, and I want all the forces which cause rotations. Well, notice AY and AX are at point A. If they're at the point of rotation, they do not give a moment. So I don't have AX or AY in this equation. I do have the 50 over here on the right, so there's going to be a force of 50. And what's the distance from the 50 to point A? Perpendicular distance, remember. 50 is pointing upward, so it's a vertical force, so I need the horizontal distance. The horizontal distance from the 50 to point A is 2 meters. Before I move on, is this a positive moment or a negative moment? Well, the way you figure it out is you put your finger right at point A, like it's a bolt or a hinge or something, and then you push up where this 50 is. And which way does this board want to rotate? Well, obviously, if I push up on this side, and this is where the point of rotation is, then my system wants to rotate clockwise. So, clockwise rotations, I've chosen to be negative, so that's a negative moment. All right, so the 50's done. The next one I see is the 100. So there's going to be 100 times the perpendicular distance from A to the 100 is 3 meters. Again, is this positive or negative? If I put my finger at A and I push down at the 100, which way does the board want to rotate? Again, it wants to rotate clockwise, so he's negative. Next, I've got the 20 over there at B. So there's a 20 times the distance from A to the 20, which is from here to here is 3, and then 3 plus 5 is 8. So the total distance of 8. Is he positive or negative? Well, my finger's at A, I push down at the 20. Again, it wants to go clockwise, so he's also negative. Any other forces? There's one more force, the reaction at B. By is a force. So there's going to be the force of By times the distance from A to By is 8 again. By points up. That upward force makes this thing want to go counterclockwise, so he's going to be positive. And that's all the forces which give rise to a moment. The 50 will, AX will not because it's at A, AY will not because it's at A, the 100 will, the 20 will, and the BY will. So, those are all of them. Add them all together, set it equal to 0. And now, of course, I want to solve for BY. So what do we get? I get minus 100, minus 300, minus 160, plus 8 times By is equal to 0. So this tells me By is 560 over 8, which is 70. Notice I got a positive answer. The positive answer means the direction I chose was correct. Which direction did I choose? I chose By to be upwards, so he's up. So there's my first answer. I now know that the reaction at the roller, point B, is an upward force of 70. Good. 2 more to go. Next one I'll use, let's try sum of the forces in X is equal to 0. Alright, so now all I want are horizontal forces. So let's see, what do I have? I've got AX to the right, so positive AX, and that's the only horizontal force here. Alright, so easy, AX is equal to 0. There is no horizontal reaction at A. So, last equation, sum of the forces in Y. What do we have? 50 up, AY up, 100 down, 20 down, and BY up. So plus 70 is equal to 0. So there's my equation. And what do we get? Let's see. 50 minus 100 is 50. 50 minus 20 is 30. 30 plus 70 is 100. I'm sorry. 50 minus 100 is negative 50. Negative 50 minus 20 is negative 70. Negative 70 plus 70 is 0. So this tells me, believe it or not, AY is 0. So just by pure chance, both reactions at A happen to be 0. Complete coincidence by the numbers I happen to choose here, but that's what the math says. That I could actually take that pin away and the system would be exactly the same. So that's a pretty interesting fact. If you're going through analyzing a system, if this were me at an engineering firm, I'd say, well, look, if this is how the system is, and it's going to remain this way, then theoretically, you don't have to spend any money with that pin. Just don't put the pin in, and it's going to remain in equilibrium by itself. You still need the roller, because the roller has a reaction, but the pin doesn't do a dang thing here. So pretty interesting. But this is how you solve reaction problems. You have your system. You look at the supports, and you figure out what types of reactions can exist at these supports. At the end of the day, you're going to get 3. Because that's the most number of equations you have. You only have 3 equations to work with, so you better only have 3 unknowns. So you're likely going to have 3 reactions. Once you know them, then you start with the sum of the moments equal to 0. Choose a point of rotation that gets rid of the most number of unknowns for you. And then calculate your moment equation, and you'll find one of the reactions. Then you move on to the force ones, and you'll get the other 2. All right, let's try another example. Let's try this. Okay, this little thing here is called a truss. And it's kind of like a frame, a support frame or something. Let's say I've got a pin over here, a roller over here. This will be point A, B, C, D, E, F, and G. I'm just naming the little vertex points, and in the next chapter, when we analyze a truss, that'll be more important. What else do we know? All I know, here to here, let's call that 4 meters. 4 meters. 4 meters. 4 meters. And from here to here, call it 5 meters. And then we'll put our load in. Let's say there's a load at E of 100. Load at G of 100. And a load at C of 50, pointing to the right. All right. So here's our example. Calculate the reactions. So, as usual, my first step is let's look at the supports and see what are the available reactions. At A, there's a pin support, so there's going to be a vertical reaction, AY. And there's going to be a horizontal one. I'm going to call the horizontal one pointing to the left. And the reason is because I see that there's a horizontal force here that points to the right. So obviously, if I want to balance it, likely the reaction at A will be to the left. All right, so those are the 2 reactions at A. What about at D? D is a roller, so there's only a perpendicular one. So I'll say there's a vertical reaction called dy, and he'll point up. So there are my 3 unknowns, AX, AY, dy. And as usual, I'm going to go ahead and calculate them. I will start with the sum of the moments, equal to 0. What's the point of rotation? The point of rotation is that vertex, or that point, which has the most number of unknowns. In this problem, A has 2 unknowns, so I will choose point A. And again, counterclockwise will be positive moments. So let's start. First of all, AX and AY, they're at A, they don't give me a moment. So they're done. First force I see is at E. It's a force of 100. It's a vertical force, so I need the horizontal distance from A to E, which is 4 meters. And then, if A is my point of rotation and I'm pulling downwards at E, this truss wants to rotate clockwise. Clockwise gives me negative moments. So he's negative. Next, I see G has 100, so 100 times the horizontal distance from A to G, which is 4, plus 4 is 8, plus 4 is 12. Positive or negative, 100 over there pointing downwards makes this clockwise, so he's negative. Next, I see the 50, so there's going to be a 50. The 50 is horizontal, so I need the vertical distance from A to C. So I need the distance from A to C, but I only need the vertical component. And so from A to this horizontal line at C is 5 meters. Remember, when you're doing moments, when you're doing torque, the force and the distance have to be perpendicular. So if the force is a vertical force, you want the horizontal distance. If the force is a horizontal force, you want the vertical distance. So from A up to where C is 5 meters. Okay. C, does that make me want to go clockwise or counterclockwise? Well, again, if I'm holding in place at A and I pull to the right at C, that makes us still want to go clockwise. So he's also negative. Lastly, there's one more force, that's dy. So there's going to be a force of dy times the distance from A to D, horizontal distance, is 4 plus 4 plus 4 plus 4 is 16. Is he positive or negative? Well, if I pull up at D, that makes this truss want to go counterclockwise, so he's going to be positive. Those are all the forces that can cause a moment for my system. So set it equal to 0. And now I can start solving for dy. I get negative 400 minus 1200 minus 2500 plus dy times 16 equals 0. So dy is going to be 374100 over 16, which, if you get your calculator out, is 256.25. So, positive answer. That means the guess of his direction was correct. What was his guess? His guess was up. So the reaction at D is an upward force of 256.25. All right, so the moment calculation is done. Now we do the other two. Sum of the forces in X equals 0. What do we have? Let's see, AX is pointing to the left, so minus AX. Do we have any other horizontal forces? Yeah, we have the 50. Points to the right, so he's plus 50. Any other horizontal forces? That's it. So equal to 0. So this tells me AX must be 50. He came out to be positive. Positive means the guess was correct. My guess for his direction was to the left. So this is a leftward reaction of 50. All right, one more to go. Sum of the forces in Y is equal to 0. What are all my vertical forces? I've got an AY up, so positive AY, 100 down, 100 down, and DY up, which is 256.25. Those are all the vertical forces. Set it equal to 0. So what does this give me? Let's see, 256.25 minus 200. I get AY is negative 56.25. Well, that's interesting. That means because I got negative, my direction that I guessed was wrong. I guessed AY to be up. So, what do I have to do? Well, make him positive. So positive 56.25 and call him down. Okay, so no big deal. If you don't know the direction and you guess and you happen to guess the wrong way, the number will come out to be fine. You'll just get a negative sign. So how do you fix it? Well, make the negative positive and change the direction. I originally thought it was up, so now I know it's down. And there you go. Again, exactly the same method of solving as every other example we've done. Here we had horizontal forces and vertical forces, but you can see it doesn't change much. He's still doing this moments. You're doing some of the forces in X. He's doing some of the forces in Y. Now what you have to do is practice these problems, do a whole bunch of examples until you get bored with it. Because the moment you get bored doing this is the moment you know how to do this very well. If it's not tricky, if you don't find it complicated, if you're like, yeah, I do this every single time, I do it the same way, that's when you know you understand it. Because the next chapter, as I said in our previous lecture, this is the first step. Once this is done, what we're going to do is try to figure out what are all the forces in all of these beams. How big is the force? In which direction does it point? And all of that. So that means how many answers would we get? A, B, B, C. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This problem would have 11 answers for what we're going to do next time. But in order to start finding those 11 answers, you must first do this. Calculate the reactions. Because you need the information of the reactions to solve for the rest of the problem. So I can't stress enough to you that you really need to practice this and make sure you have it down pat. You will not be able to do the next set of problems if you can't do this. So if you're having trouble with them, if you're trying to practice problems and you're not getting the answers I got on the solutions, or you don't really understand how to go about doing it, email me, talk with me, and we'll work our way through it. But you have to be good at this, so practice them. Anyway, I hope this was helpful to get a few more examples in, see how to work these problems, and until next time.